language processing with a focus on computational pragmatics, meaning language and use. At CSATS, we have been very grateful to partner with her with some summer programs. We have a program this summer that she will be running with some teachers. So if you are interested in that, feel free to reach out to me at CSATS and we will get you connected. So without further ado, I'm going to stop my screen sharing and you are good to go. Got to unmute.
Thank you. Okay, so I was saying hello to everyone, and I'm going to share my screen where you'll see this presentation, Machine Learning for Formative Assessment of Students' Writing. So let me go into slideshow. There we go. Okay. Yeah, so I'm going to talk in a very nitty-gritty way about one of my research interests, which is applying automated methods to analyze students' writing in STEM subjects. I should have capitalized STEM on that slide. So here are a list of subjects and different types of STEM writing, where the goal is to look at the writing automatically to determine whether students can explain science ideas in their own words. And the objective of the NLP then is to assess the content of the writing, not to assess the mechanics of the writing. And I'll be talking about work that's been going on in my lab on assessing essays, constructed response questions. That is where instead of a selected response like true or false or multiple choice, the student has to write the answer in their own words. And a college statistics set of these CR questions where there will be multiple questions that go with a given scenario. And then finally, lab report for college level physics. But I'm also going to include some of our work that kind of covers all of this, which is human in the loop methods. So I appreciate that Mehrdad kind of mentioned that near the tail end of his talk. So this is a web-delivered roller coaster curriculum for middle school students, just showing some of the screens that they can page through, where they'll have a roller coaster simulator in which they can do experiments. They need to record data like, does the cart, when it moves down the hill, get up the next hill? And if so, what was its weight? What was its maximum speed? Those kinds of things. Then the student will answer some of these constructed response questions and is then prompted to write an essay. So the first essay in the challenge number 1 of this curriculum prompts for these 6 main ideas. So they're not told the main ideas, they're learning these main ideas. They're prompted to do things like, don't forget to mention the relationship between height and potential energy. And the example question over here is also one of the constructed response questions that they get about these kinds of ideas. So they're writing the ideas in response to questions before they even get to the essay. So what do we try to do with the essay? Well, the idea is to just automatically detect whether the essay mentions each one of these 6 ideas. And actually, I'm going to jump ahead to just show you the screenshot. They get a checklist feedback that I'm going to return to in a minute. So our goal then is to detect the presence of ideas, by which we mean full propositions or statements of the law of conservation of energy, for example. PureEval is the tool that my lab has developed. It's a lightweight software tool, and it's very lightweight because it does not use language modeling and it doesn't have to be trained. It relies on a previously trained weighted matrix factorization method for semantic vectors, where it has a very large vocabulary, and we've kind of tested this quite a bit against other ways to create these vectors. It works very well. All we need is 5 good examples of the kind of passage the student is supposed to write, and then most of what happens after that is automatic. So we don't need the training data, which is good because the curriculum for this project was developed during the project. My collaborators are in the learning sciences, and they study how to create good curricula and how to scaffold students' learning in a variety of ways. So the important thing is that idea importance emerges from these 5 good examples. And I'll illustrate that here, what I mean by idea importance. So if, say, 3 students are prompted in the same way to write about something that they've all read about in common or studied in common, they will not mention exactly the same ideas. So each circle here in this Venn diagram is supposed to represent the student essay for 3 different students, pink, turquoise, and lavender. And most of the ideas are on the periphery of the circles where they don't occur in anybody else's essays. But there's a few ideas 2, 4, and 3, that occur in subsets of 2, and then one idea that all of them mentioned. So we actually use this weight, this number of the reference passages that mention the same idea as an importance weight, and that turns out to work quite well. We've actually spent years looking at how well this method can generalize to assessing humans' ability to summarize, machines' ability to summarize, and so on. So this is a picture of our architecture, which I'm not going to go into a lot of detail about, but you'll notice over on the left, the input is the reference summaries or the student summaries or the essays, if it's looking at essays. The pre-processing takes all the essays, the reference passages and the student passages to be evaluated, and converts the written text into a list of semantic vectors where each vector represents one of the clauses in the essay. For the reference passages, one algorithm called EDUA just groups all the similar statements together to see how many of them were mentioned by all 5, how many of them were mentioned by some subset of 4, and so on, to create this weighted list of the ideas. Then this other algorithm called WMIN matches the propositions or the proposition vectors from the student essays to that model and assigns that weight, and then sums that up to determine how well the student did. But what we're mainly interested in is, does the student mention the idea? And here I want to just take a moment to say that the role of the automated feedback is not done when it just provides this checklist. It's supposed to create opportunities for the student peer pairs to discuss the feedback and look at the writing, for the teacher and students to discuss the feedback and look at the writing, and help the student prepare to submit a revised essay. And in this curriculum, which we've looked at for 2 years in classroom settings with many classrooms in middle schools in Wisconsin, students nearly always show improved understanding in the revision. And this whole process of writing the essay and getting revision after the students have written answers to questions, and then they write a second essay with more ideas, that would be infeasible for the teacher to handle with all this assessment without the automated support. So now I'm going to turn to the questions, the constructed response questions, but I'm grouping it with the middle school physics with the college statistics because the same methods apply to both. So here we use relational neural networks. We were inspired to do this from the use of relational networks in computer vision, where relational networks are used in order to understand relationships among objects in a scene, for example. But one of the things about relation networks is that they're highly efficient. And also in language, a lot of the useful meaning is actually relational. And these kinds of networks are more efficient than the currently very widely used attention networks and transformer networks. And the goal for the constructed response assessment is not to give a grade, but to give this 3-point scale of correctness feedback. Is it correct, partially correct, or incorrect? And that helps teachers and students identify which students need relatively more help and what kind of feedback to give to students who are partially correct, for example. So I'm going to talk about two relational networks. One's a flat relational network, and one is has a very complicated structure. So let me get to the flat network first. Here, what I'm showing is a question. Susan has samples of 5 different foods, et cetera, et cetera. How will she know which food contains sugar? There's a reference response, and then there's the student answer. And the color coding is just to indicate that there's words that occur in pairs of these 3 items, and some words that occur in all 3, but that kind of is meant to illustrate that there's different kinds of relationships among the wording across these 3 texts that are part of the whole assessment process. So what we do is we turn the question into a vector, first encoding it, and then the reference answer, and then the student answer. And it just learns a single relation that could be the same dimensionality as these vectors for the question, reference answer, and student answer before it decides was the student correct or not. So here is more specifics on this relation network. Again, the text for the question, reference answers, and student answers are first encoded, and we use BERT fine-tuned encodings of each. Then the relation vector is learned, but if for one student answer and one question prompt, there will be multiple reference answers, at least to exemplify each correctness class, but there may be even more than that. So for that one student answer, these relation vectors then get fused together through another learned process, and then the correctness is classified. And this works very well. So here are some benchmark data sets where the bold facing for SFRN+, which is with the BERT encodings, outperforms many of the baselines at the state of the art at the time and our own other baselines. Beetle is an electronics domain, so it's very uniform. The science benchmark data sets are multi-domain, and the tasks get harder and harder. Unseen answers, unseen questions, meaning the model has never seen these questions before, or even unseen domains. But now I'm going to turn to this somewhat more novel issue for short answer assessment, where there's even more textual components and their interrelationships. The context that sets up a whole setting where there might be multiple questions, followed by the rubric that maybe a human assessor uses. The human assessor may also use reference answers, and then there's the student answer. Well, so there's all these different kinds of text that need to be related to one another. And here what I'm showing next is these arrows. It didn't come up quick enough, so I put too much on the slide. Anyway, these arrows each show a learned vector between 2 nodes, the context in each question. Then that learned vector is sent down to connect to the vectors below it. So there's this kind of dependency structure rather than connecting every node with every other node. And we tested this extensively, and the dependency structure that more reflects our understanding of how these things are related together actually performs the best in assessment. It motivates a recurrent relation network in part because we call these arrows where the vectors are being learned message passing among the nodes. And it takes a while for the model to actually sort of do all the message passing and stabilize. So it's done over multiple time steps. And then also in order to sort of stabilize the information flow, we add a super node, which is the red node up here. So this picture has the rubrics. Here we don't show the rubrics. We just show in these dashed boxes one of the graphs with the context, the question, the reference answers, and the student answer in the super node, which is the red circle. And then the dashed boxes over time are just these time steps. And then far right, we get out the result. And we also use contrastive learning, which I probably won't go into here. But contrastive learning helps develop representations that are close to similar things and that are far away from dissimilar things. And that means that we can use the reference answers to try to find the most similar partially correct reference answer to give students feedback. This just shows that this model performs very well. And there were all these different experiments to ablate parts of the model. And the full model that I just showed you with the contrastive loss is the one that performs best. It also outperforms all these other large language models. It outperforms SFRN, our previous flat model. It also outperforms GPT 3.5 with prompting, with in-context learning or not. It far surpasses what GPT-3 could do, and that may be in part because the language that the students are using is it's not a fully developed language. It's not always all that articulate. Now I'll just say a few words about the college physics lab reports, where our method adapts open domain question answering in order to apply very detailed assessment rubrics with multiple dimensions. That makes it an analytic rubric where each dimension is then assessed on a 0 to 5 scale. So here's what I mean by the analytic dimension. So here's a dimension for the pendulum report, which is about conducting experiments on the behavior of the pendulum, and then another report, force in motion. You can see that the rubric that has this 5-point scale from 1 to 5 for any points, or 0 if they say nothing relevant, you could either list out different ways the student could answer, and the rubric says select one of these that most closely explains how much information the student included. Or this other dimension says, here's all, a list of things that the student could get 1 point for, and sum all of these, and then that would be the student's score for that dimension. That makes the rubric dimensions very challenging to apply automatically. And our method is inspired by open domain question answering, where there's 2 modules, where the first one is just responsible for determining, well, is there an answer in this document? Why do I say answer? Well, the question answering part is that we're treating each rubric dimension as the question and the report as where there should be an answer to that question. So there's the verifier module that just decides, is there an answer? The grader module then uses this special log loss, the ordinal log loss, that takes into account that a score of 5, if you meant to give a score of 4 and the model got it wrong and said 5, is not a big error. But if the model says 5 and it should have been a 2, that's a big error. That's what's meant by ordinal loss. So this is an architecture picture of that model. I guess the only thing I'll mention is that it uses 2 encoders, one for the rubric and one for the student text. And then, it verifies, then assesses. And that's in order to give students very good feedback as to how well they are addressing that analytic rubric. And they don't see quite as much detail in the rubric they get. It's more like a sort of prompt that encourages them what they're supposed to include in their essay. And you can see we compared Veras with several different baselines. And Veras outperforms on the total score for the discussion section, where each dimension is first scored, and then you sum the score for each dimension. So mean squared error should be lower to be better, and Veras has the lowest mean squared error, and the other metrics should be higher to be better, and it outperforms these other methods. And that's important also because the TAs actually are not consistent with one another in this very large physics class that this data came from across different sections, whereas an automated system could be consistent across students. Now I'll just say a few words about how humans could be combined with machine effort in one particular way that we call selective prediction. What selective prediction means is that we could have a classifier, and besides its decision, it produces probabilities for the classification that it makes. So if there's these 3 classes, partially correct, correct, and incorrect, it would give a probability for each one of those that needs to sum to 1, and that's called the softmax output. So if the most confident, the highest probable class picked by the classifier is 99%, and the remaining 1% is distributed over the other 2 classes, that means the model's pretty confident. So you probably want to go with the model. But if the highest class is 33%, that kind of means the model can't decide between that class and the other 2, because then they would all have to be 33%. And that means the model's not confident. You want to use the human label. And in the past, what people were doing to try to make this a little bit more rigorous is to develop methods to learn to calibrate the softmax probabilities and make the confidence probabilities more correct in a way. But what we decided to do was to try to learn from the machine learning classifier's behavior when to defer. And our first method worked pretty well, but then we decided we should learn both modules together. And that's what we did here. So step 1, we first trained a classifier to classify the correctness of the model at deciding, is the student answer correct, partially correct, or incorrect, 0, 1, or 2. Then we freeze those parameters for that model that's been partially trained. And we use it while we're training our initial pass at a deferral policy, which encodes the same input that goes to the classifier. But then the classifier for the deferral policy also gets another input, which is the learned vector from the classifier. Sticks those together, and then it makes a decision at its classification layer whether to defer or not. And so it learns for a while. Then we unfreeze the classifier and have them learn together so that there's this one vector that they're both sharing, and they're kind of learning that together. And this allows the deferral policy to kind of learn about the classifier at the same time. That's an advantage because the other methods I mentioned need an entirely separate data set to train this calibration method that has been used in the past. And we don't need to use a separate data set. We just train these 2 models together so that they can kind of work well in tandem. I won't go into any more technical details about how we do that. I'll just say that on 4 constructed response data sets, including the middle school, with 3 strong baselines and lots of ablations to see, can we leave out any parts of this model and will it perform just as well? We found that the model I just described outperformed all the baselines. It had higher accuracy and much lower deferral rates, so that is much less human effort. And I'm going to conclude, hopefully leaving just a few minutes in case anyone has questions, to say that the kind of work that I've covered here really aims to support classroom instruction in a way that helps teachers do what they want to do and like to do better. AI should not be expected to be perfect, but it does have great potential benefit. We've seen these demonstrable results for the middle schoolers learning science, where they actually are learning more science when they can revise their essays and get immediate feedback. That's not the only thing that helps them learn more science in this curriculum, but it certainly helps. Then with the statistics project that I mentioned, we're actually in the process of collecting data from partner institutions all over the US, with very diverse student bodies, including Hispanic serving institutions, so that we can be sure to develop our technology to perform equally well on students from all diverse backgrounds. And I had mentioned before that the TA assessments of the physics lab reports, we know we're not consistent. We have some published work on that, but it also, because it's inconsistent and it's not really quite correct, it leads to incorrect conclusions about where students have difficulty relying on the TAs, because TAs are not really trained to give the kind of feedback that would help the students, the college students, learn physics better. And it also presents to the instructor an incorrect trend line across different reports. So it made it look, looking at the TA grades, as if students were actually improving over the course of the reports, which is what the instructor wants to see, but in fact, they were not improving. So that's the end of my presentation. I guess I could stop sharing then.
Thank you so much, Becky. Questions out there? And again, I put in the chat links that you can come and join us this summer with Becky's amazing work. We had rave reviews from the teachers that participated last summer, and we'd love to have more interest this summer. Becky, would you mind putting, if you're interested, your contact information in the chat?
Oh,
Jay, there's also one question. Do the tools also account for group activities like middle school labs?
Well, I'm not quite sure exactly what you mean, but in that middle school curriculum, there's a lot of peer-to-peer activity. And students assess each other's essays, as well as looking at the essays with the teacher, because they're kind of checking the automated feedback to see if it was correct. And that's actually something that in the learning sciences that they were very excited about, because it allows in the classroom the teacher and students to really pay attention to how the students write down a given idea. And it's very hard to instruct students in what it means to revise. And so I think they're getting a much earlier sense than they would otherwise. And they are working in peer groups in the classroom while they're taking this curriculum. It is not meant for the students to go through the curriculum on their own. It's all kind of semi-structured group activity with the teacher helping them through the curriculum and setting up activities that they do in small groups. I hope that answers your question.